Hi, this is Tim Mulrooney from the Department of Environmental, Earth, and Geospatial Sciences at North Carolina Central University. This is my presentation entitled Semi-Automated Procedures to Assess the Quality of NCDOT GIS Data. This was through a North Carolina Department of Transportation research grant that was headed up by myself and my graduate assistant Glenn Koch and a graduate team, a team of graduate and undergraduate students that I'm going to show in a little bit. This was a pretty neat project that we started to look at the actual quality of NCDOT GIS data. And before we talk about it, I'll mention a couple of things. When you go to the NCDOT GIS database, the GIS download section, there's a number of different files that you have there, personal geodata or geodatabases they have. There's one called the LRS ARCs, and that contains about 200,000 individual features that are basically sections of road, and they're linked to more than 400,000 road characteristics that are related to these LRS ARCs, and they're needed when the road attribute changes. When we looked at the NCDOT GIS data originally, it's represented using about 93 different attributes. We're going to talk about the 23 high priority ones that we needed to check out. But as you can see, here's a section of road where we have multiple instances of road characteristics change, where we have structure type. And along a section of road, if a road characteristic such as the speed limit or turn lane or structure shape changes along that same section of LRS ARC, it needs to be represented using a road characteristic. And so you can imagine all the challenges that we have in trying to assess this GIS data and map the actual data quality. Now, the reasons why we need this QA/QC and the reason why the NCDOT came up with the idea for this project is, first of all, the most obvious is liability issues that exist with the publication of poor quality data. The other things that we started to address were the issue that there's been no quantitative assessment of data that's been done on that. And when we went through our literature review, there's been very little review or work on the whole idea of mapping data quality. We've talked about, we've looked at some things at data quality assessment, but mapping to see if there's any spatial autocorrelation with the actual data quality, and we're going to show that today. In addition, there's been legacy information about the data. It really hasn't been retained, so we don't have feature level metadata that are few. If we do have it, it's really few and far between. And the most important thing to the DOT, there's been very little research or uniform methods to evaluate dimensions of data quality that fit their needs, because a lot of this data was created in the past, but it's also being created now with QC controls in place that make sure it has the correct attribution and lines up correctly in photo revision efforts. So we're trying to marry the older data and the new data and trying to basically give the NCDOT places to start where where data development or redevelopment efforts kind of would best be started. When we looked at the actual components of data quality, we saw three different components that we were able to measure within the scope of this research. The first one was horizontal accuracy. That's probably the most obvious and probably most pressing for a GIS professional, but it basically measures where the GIS data layer should be, and we compared it to the NCDOT imagery, the imagery provided by North Carolina OneMap. So you can see what it looks like here, and we can actually go through and measure this, and I'll talk about some of the techniques that we use to measure this. The other component of data quality was attribute accuracy. It describes how well the assigned attribute matches the actual characteristics according to the LRS ARCs, and then for us, more importantly, was those road characteristics that I talked about that are subsections of those LRS ARCs. And the DOT identified 23 high priority attributes for us to check. You can see left turn lane here is one of those. It can only be one of 5 possible values, and we needed to confirm that using the imagery. The other component of data quality was attribute completeness. So we looked at about 34 different attributes to make sure they were actually complete. That didn't necessarily mean they were correct, just to make sure they were complete. So for like the turn lane type, the only possible values there could be 0, 1, 2, 3, 4, 5, or null. Those are the only possible values. It couldn't be 8 or 10 or anything else. For the right of way, it had to be a number. For the surface width, it had to be a positive number. Nothing more, nothing less. It couldn't be a letter. It couldn't be a negative number or zero. So we went through and we automated some Python code to look for this attribute completeness. There are other forms of data quality. There's logical consistency, temporal accuracy, but basically they fell outside of the confines of what we were trying to do here for the NCDOT. Now this was our research team right here. So this was me. Glenn is the upper right there, and these are our undergraduate students that we worked with, Roderick, Ed, and Corey. So this is our research team, and this was over the 2013-2014 school year, with a lot of the work being done during the summer of 2014, and we've been kind of completing the last of it in the last 6 months or so. Now, when we wanted to measure the actual horizontal accuracy, like I said before, there was 200,000 LRS arcs, and as you can imagine, with all 5 of us, we didn't have the time to measure all 200,000 of those. So we selected the total number from the number of LRS arcs at each county according to the ANSI Z 1.4 1993 standard. So for every county, we created 100 county level databases from which we worked, because we're going to make maps at the county level so we could dictate which counties had the best quality, lowest quality, and where they should basically dedicate development or redevelopment efforts. So for smaller counties, or basically counties that had less LRS arcs like Hyde and Tyrell, we picked out 50 randomly selected LRS arcs all the way up to 315 LRS arcs for Wake County. So for the entire state, we measured approximately 11,500 LRS arcs that were under the purview of the NCDOT. So this didn't include like ramps or local roads. So we kind of queried those out and only picked the ones that were of importance and under the direct purview of the NCDOT. Now, today I'm going to focus on my horizontal accuracy and how we use this using these semi-automated techniques, because to measure horizontal accuracy going into this, we really didn't have any idea, and the NCDOT didn't really know what they want or the actual processes for what they wanted. So the first thing we needed to decide was, well, how do we measure accuracy? Because as you can imagine, as you traverse along a road, it's going to kind of waver in and out or go closer or further away from where it actually should be, as you can see in the image to the right. So what we decided was that there were 3 points equally placed along an LRS arc. So for, say, Wake County, we had 315 of these LRS arcs. For Alamance County, we had 125 of them. So we were going to create 3 times 125 points that needed to be digitized. And to create these equally spaced arcs, we actually there was a tool, and we did this in Python code. And I'll show this in a second. Now, the next thing, the research team actually had to digitize the points along the true road imagery. So as you can see, point 1 right here, our research team had to actually digitize that closest to point number 2, which we created using our Python code. The next thing we needed to do for all these points, so for, say, Alamance County, for those 375 points that we created, they were basically joined or aligned with 375 points along the center line. We had to measure those within a GIS. And we also did that using the near function. We automated that in Python code. And then we grouped that at the feature level. So for each of these 125 arcs in Alamance County, we figured out which one had the best average horizontal accuracy. And then we grouped that at the county level. And you can see what we did here for this Create Lines from Toolbox. And this is a nice tool that I found on the ArcGIS website. You can specify the percentage. I specified it at 0.25, and we didn't specify endpoints, and these were the requirements dictated by the NCDOT. So what it did was it created 1 point at the midpoint and 2 points halfway between the endpoint and the midpoint in each of the 100 databases with varying number of LRS arcs. So you can see an example of what we're looking at right here, and this was a really powerful tool. You can see here, this is an example of the Python code that we did this. And we did this, we created these points right when we created the actual database. So a lot of the code up at the top just talks about how do we create the actual database, make sure it's created. I think we created GDB's file geodatabases in this case, and you can see I imported the tool all the way up the top right here because this was in custom code right here. And then down at the bottom, you can see me that I highlighted in red, me calling up the actual create points along lines with the input parameters that were required. So you can see what we had here. Now, the next thing that we needed to do was for each of these individual arcs, we had to measure these distances right here. And for maybe the first day or so, we started to actually measure the distances and kind of collect those. And we figured there had to be an easier way to do this. And we also found this in Python code. And this is using the near function. So we tried to integrate the near function in this. So you can see the Python code. This is a really powerful script that did 3 things at once. The first thing it did, it went through all 100 databases. So you can see up at the top, Python, when we do looping structures or control structures, it did this, you can see they're indented to the right, but you can see it did this for every single database. Now, between us creating the 3 points and us running this code, our students had to go through and digitize every single point along the road center line. So that took a few weeks for us to do. You know, our 4 students, 5 students, me included at times, going through and digitizing these. But after we did that, we did something really powerful. We ran the near function, which calculated the distance between each point and the nearest road center line that we extracted from that prior function. The next thing we did was we just created an average for each individual arc using the summary statistics, using the summarized function. And the last thing we did all the way down at the bottom, at the county level, we just summarized each of the individual, we averaged up each of the individual horizontal accuracies to give us a county average. So for every single county, we had an average horizontal accuracy. For every single arc, we had an average horizontal accuracy. So we can look at spatial autocorrelation not only at the county level, but at the sub-county level for these randomly selected features throughout the county. And these are the results that I have. So this is a map of horizontal accuracy using these techniques. They ranged from about 0.6 feet in Davidson County to about 18 feet out in Clay County. And these aligned with highway districts, I believe there are 9, 10, and 12, where photo revision efforts have kind of taken place. And the NCDOT was happy to see that these photo revision efforts have kind of been seen to fruition, can be articulated in a map here as we run down that 5285 corridor from Winston-Salem down to the Charlotte area. In addition, and I'll mention this really quickly, with horizontal accuracy, they earned a score between 0 and 100. We did the same thing with attribute accuracy, where basically students had to check the individual attributes for right turn lanes, right of ways, and all these other 23 high priority features. And we also did that for attribute completeness, where I just created a big, about 500 line Python code that just went through every single individual attribute to see if it was correct. I wanted to focus this on horizontal accuracy, and you can see for Stokes County, we averaged up the horizontal accuracy score, the attribute accuracy score, and the attribute completeness score to get a final score, which is just the average of the 3. You can weight them whatever you want, but the NCDOT just asked that they be equally weighted. So Stokes County had a score of 88.2, where the horizontal accuracy was 99.2, attribute accuracy contributed 92.1, and completeness contributed 73.3, all the way down to Craven County, where the horizontal accuracy earned a score of 13.9 out of 100. Attribute accuracy was 24.5 and completeness was 40. So I write, excuse me. So I wrote a number of other Python, I wrote some other Python codes to calculate attribute accuracy and attribute completeness. And this was the final score by county. So you can kind of see the maps that we made for final score. You can kind of see here in the Research Triangle area over in Orange and Durham County and Alamance County, they were relatively low. So there is some spatial autocorrelation. And I ran some geostatistics on those that I can talk about at another time. But in conclusion, Python's a really powerful programming language, and we automated our GIS functionality like the near function and the summarize with repetitive processes. We created models at first using near functions and summaries, and we exported those to Python codes, and basically we integrated our own control structure so we can do this for 100 databases at a single time. And then we can also output summaries or logs to CSV files. So like I talked about with the attribute completeness, I exported all 1 million errors of the attribute completeness errors to a file that the NCDOT could assign someone to do at some point in time. And then, like you saw before, all forms of error are spatially autocorrelated, and the reasons for these patterns vary. So I just wanted to thank the folks at the NCDOT, Jonathan Arnold, Ashley, Tim, Faith, and Mustan for their help in helping to facilitate this project. And that's about it. Thank you very much.